Hi, welcome to Introduction to Gases. We're going to talk a little bit about what a gas is, as well as how gases behave at the molecular level. And we'll wrap up by talking very briefly about the difference between an ideal gas and a real gas. Okay, so with that, let's get started. What is a gas? You know that a gas is amorphous. It has no definite shape. You know that a gas has no definite volume. You know that gas is one of the four states in which any substance can exist, a state of matter. Okay, so you've established that, but what is a gas really? Well, to talk about what a gas really is, we're going to have to talk a little bit about something called the kinetic molecular theory of matter. It sounds serious. Well, as a matter of fact, it's pretty simple. So you know that kinetic means moving. And molecular, you know, means small units of matter. And matter, well, you know that that's just all the stuff around us. And you also know that in science, a theory is something that has lots of evidence to back it up and that's been repeatedly tested and hasn't really found anything that knocks serious holes in it. So the kinetic molecular theory of matter, you might be surprised to know, you already know. The kinetic molecular theory of matter just states that all the matter around us is made up of small pieces, that'd be the molecular part, and that those pieces are in constant motion, that'd be the kinetic part, and that the motion of those pieces increases the more heat or energy you add to them. So, the particles in a solid, as long as it's above absolute zero, are moving, but they're locked in place, and they're moving relatively slowly. While the particles in a liquid are moving more rapidly, more freely, they're no longer locked in place and are able to slide past one another. And the particles in a gas are moving very rapidly, are definitely able to slide past one another and move very freely. And then we have that other state of matter, plasma, which is like a gas, but we've lit it on fire. It glows. Okay, so that's really all the kinetic molecular theory of matter is. How does that relate to how gases behave? Well, that's what we're about to discuss. So when we talk about kinetic molecular theory of matter as it relates to gases, and we'll just call it KM for short, we first have to think about what we'll call an ideal gas. An ideal gas? Well, it's perfect. And as you might guess, we can talk all we want about ideal gases. The gases don't always behave exactly the way we want them to as ideal gases. But for the purposes of discussing how gases behave in KM, or kinetic molecular theory of matter, we're going to go with 5 basic assumptions. Remember, these are just assumptions. They don't always hold true, but most gases behave closely enough to these assumptions that we can kind of fudge the numbers. Our first assumption is that though gases do consist of very large particles of numbers, those particles are very far apart from one another relative to their size, and that most of the space that's occupied by a gas is actually empty space. This explains why we can compress gases, such as you might have done if you've ever used a manual bicycle air pump, and it also explains why gases are so low density. When you boil off a liter of water, that liter fit easily in a little 1-liter bottle. The steam that you produce from that can fill a very large container. Again, gases are very low density compared to the liquids from which they typically come. The second assumption about how gases behave, according to the kinetic molecular theory, is that when gas particles collide with other particles or with their container, such as the wall of a balloon, or the wall of a room, or the wall of a cylinder, those collisions are what are called elastic. That basically means that neither particle slows down. Nothing changes its velocity. So it means that kinetic energy does get transferred, but none is lost as long as we don't change the temperature. Think of a bunch of pool balls colliding in a chain reaction, except that none of them change their energy. and whatever velocity any of them have going into it, they maintain going out, so no kinetic energy is ever lost. We assume that gas particles behave that way. We assume that gas particles are in continuous, rapid, and random motion, and therefore have kinetic energy to begin with. This helps explain why they keep moving and don't lose anything, because we assume that the kinetic energy they possess is high enough to get right over any attractive forces between the particles. It's kind of as though you're running through a party, and no matter how interesting that person who's standing still might be, no matter how attractive they might be, and how much you might want to talk to them, you're just running too darn fast. You're going to run right past them. Zoom. This kind of relates to the last point. Kinetic molecular theory, as it applies to gases, assumes that there are no forces of attraction or repulsion between two gas particles. So, when two particles collide, there's no temptation to stick together. They immediately bounce apart, partly because of their high kinetic energy. And the last assumption that we make about gases, when we talk about them in light of kinetic molecular theory, is that the average kinetic energy of gas particles depends on their temperature. So, if you recall, for any object, whether it's a brick, a cloud of oxygen gas, a lump of lead, or a nice pond full of water, any object, kinetic energy is equal to 1/2 the mass times the velocity squared. I guess for the object it would be the particles in the pond, but anyway, mass is m, v is velocity. So, because temperature is really a proxy for kinetic energy, so again, for two gases that are at the same temperature, their kinetic energies are equal. Well, if their kinetic energies are equal, but their masses are different, it means that their velocities have to be different, because kinetic energy is described by that equation. So, at the same temperature, little tiny light particles tend to be moving faster than big, heavy particles. You can think about this as a Honda Civic full of cotton balls zipping right past that semi-trailer full of cinder blocks on the highway. How do these assumptions explain the behavior of gases? Well, according to those assumptions, gases would fill their containers. They'd take its shape. That's true. According to those assumptions in kinetic molecular theory, gas particles should be able to slide right past one another and behave very much like a liquid. That's true. Gases and liquids are both considered fluids. That would also explain why they're so low density, typically about 1,000th the density of the same substance in liquid or solid state, and why they're so compressible. This also explains why gases randomly mix with other particles until they're distributed pretty evenly. What we know is that lighter gases do diffuse more rapidly than heavy ones, and that fits right in with the idea that lighter gases would have higher average velocities at the same temperature, higher, that is, than a heavier gas. The very last point in terms of gas behavior and the kinetic molecular theory is effusion. So this is when gas particles move through a small opening. You can imagine a balloon filled with air that overnight goes from a big, beautiful, lovely yellow balloon to looking like this. A little, sad, puckery remnant of its former self. That's because there are tiny openings in the skin of the balloon, and the gas particles are able to move in and out through them. The warmer something is, the faster those particles move, and therefore the faster they will move out of the balloon. It also means that a lighter gas at the same temperature as a heavier gas will effuse more rapidly than the heavier gas, again, because its particles are moving faster. Okay, ideal gases versus real gases. Pretty easy here. Ideal gases are perfect. That's right. They do exactly everything that we assume gases do according to kinetic molecular theory of matter. Then there are real gases. Real gases, well, they're real. What that means is they occasionally tend to deviate from our expectations for an ideal gas. Maybe their collisions between particles aren't completely elastic. Maybe they do lose some energy over time. Maybe they are slightly attracted to one another. We see most of these deviations under a couple conditions. First of all, low temperatures. At very low temperatures, gases are moving very, very slowly, and a lot of them are just about ready to condense. So sometimes they are moving slowly enough that they don't overcome the forces of attraction between particles, and they are attracted to one another. Sometimes they also have some forces of attraction between them and their container. This leads to some loss of kinetic energy in the process of those collisions. The other place that we see a lot of deviations is at very high pressure. At very high pressures, you're pushing those gas molecules together so tightly that sometimes that does cause them to be forced together. Again, you can condense them that way, but even before the point of condensation, sometimes you will have some forces of attraction or some slightly inelastic collisions. Okay, that's it. We talked a little bit about the kinetic molecular theory of matter, how gases behave, what an ideal versus real gas is. In the next video, we'll talk a little bit about pressure, temperature, and volume, and how they all interact to change gases. That is, to change the other two factors about measuring physical properties of gases. Have a good day. Hi, welcome to Introduction to Gases. We're going to talk a little bit about what a gas is, as well as how gases behave at the molecular level. And we'll wrap up by talking very briefly about the difference between an ideal gas and a real gas. Okay, so with that, let's get started. What is a gas? You know that a gas is amorphous. It has no definite shape. You know that a gas has no definite volume. You know that gas is one of the 4 states in which any substance can exist, a state of matter. Okay, so you've established that, but what is a gas really? Well, to talk about what a gas really is, we're going to have to talk a little bit about something called the kinetic molecular theory of matter. It sounds serious. Well, as a matter of fact, it's pretty simple. So you know that kinetic means moving, and molecular, you know, means small units of matter, and matter, well, you know that that's just all the stuff around us. And you also know that in science, a theory is something that has lots of evidence to back it up, and that's been repeatedly tested, and hasn't really found anything that knocks serious holes in it. So the kinetic molecular theory of matter, you might be surprised to know, you already know.